Hi, this is Lauren,
And Adrian.
and we're going to teach you how to create 3D forms.
We will take you through the steps of transforming a 2D polyloop into a 3D triangle mesh. The purpose of this tutorial is to teach you how to take a 2D drawing and turn it into a 3D object.
The first step we'll look at is 4-point refinement.
A 4-point refinement is a type of refinement that interpolates the control points and smooths a polyloop.
Here we'll draw the polyloop. Here you can see the polyloop and the control points. As we call the refinement each time, the control points double, creating a smoother polyloop.
The second step in the process involves calculating the Delano triangulation.
A, B, and C are the vertices of a Delano triangle if for every other point D, D is out of the circumscribing circle of A, B, and C. As you can see, the triangle on the right is not Delano because E is inside the green circle. Here is a demo of Delano triangulation involving a cloud of points. Notice how the triangulation changes as new points are created.
Here is some pseudocode that implements the Delano triangulation of a cloud of points. It is a very literal translation of the definition and has a big O of n to the fourth, so if your calculations are time sensitive, you may need a more complicated algorithm.
The Delano triangulation is helpful because 1. It allows you to calculate the medial axis transform, and 2. It relates random points in a mesh to neighbors who are unknown. This information will become useful later on.
As we just said, the Delano triangulation helps you calculate the medial axis transform, which we will now explain.
So what is the medial axis transform? It's basically the skeleton of a polyloop.
If you take a circle and shove it into the inside of a polyloop so that the edges of the circle are touching the boundary of the polyloop, then as you drag the circle around, its center will follow the medial axis transform. Notice how the center of the circle in the animation follows the blue line. This line is the medial axis transform.
Going back to Delano triangulation, the centers of the circles that circumscribe the Delano triangles will approximate the medial axis transform, like we just saw. The more refined the polyloop is, the better the approximation of the medial axis transform.
Here is the polyloop we saw earlier. Watch as we calculate the Delano triangles, calculate the circumscribing circles of the Delano triangles, and then the centers of the circumscribing circles. Look how the centers of the circumscribing circles lie on the medial axis transform. As we refine the loop, the approximation of the medial axis transform becomes more exact.
The medial axis will become useful later on as it helps us gather information to create a 3D object. For example, the information gathered will help us calculate how much of a bulge a polyloop will have in certain places, which will come later on.
When drawing a mesh, it will be very useful to store extra information about the mesh.
There are 3 basic array structures that are used in mesh representation. The first is the geometry array, which contains the points that represent the vertices. The next is the vertex array, which contains the corner vertex incidents. And the last is the opposite array, which contains the opposite corners of the current corner.
Let's take a closer look at the geometry array. For each vertex, it contains the x, y, and z values that represent it. Here's the vertex array. For each vertex, it contains a pointer to the geometry array where you can find the x, y, and z values. This is also where the triangles are stored. The first 3 values belong to the first triangle, the second 3 values belong to the second triangle, and so on. It is also important to note that the vertexes are stored in counterclockwise order.
The opposite array contains the corners that are opposite of the current corner. For example, the corner 2 has an opposite at corner 5. If the corner doesn't contain an opposite, it should return itself.
To create a mesh from our polyloop, random points will be sprayed into the inside of our polyloop. The Delano triangles will then be calculated to fill the geometry and vertex arrays. Once this is done, the opposite table can be tabulated. An example function that does this is shown here.
Here are some examples of traversing through a mesh using corner operations. The spray of random points creates a very messy mesh, but in order to smooth the mesh, we'll use Laplace smoothing. Laplace smoothing is a way to make the interior points of a mesh more evenly distributed, as it works by moving each vertex in the interior toward the center of its neighbors.
Here's an example of Laplace smoothing. Watch as the center vertice moves towards the center of its neighbors with each iteration. The repetition of the Laplace smoothing algorithm converges to a mesh that is evenly distributed. Watch the effect of Laplace smoothing on a mesh that has a randomly distributed interior.
Here is some pseudocode that implements Laplace smoothing. The next step, protrusion, will allow us to bulge the 2D shape into a 3D form. This means that we'll calculate the height of the bulge at points throughout the mesh. The height can be calculated from the radius of the circle circumscribing the Delano triangles in conjunction with the distance of that point from the medial axis.
Here we have a circle that circumscribes the Delano triangle, and the circle again rotated 90 degrees. If you calculate the distance to the nearest point on the medial axis transform B, and the radius of the circle centered on the medial axis transform C, then the height at P will be C squared minus B squared.
Watch as we move the Delano circle in yellow. As the blue circle moves with it, we start to see the outline of the 3D shape.
After you calculate the heights of all the points, you will see the shape here. Notice that it is only half of the shape that we really want. To get the shape we really want, we will have to compute the mirror image.
To obtain the mirror image, copy all the vertices and make their z-value negative. This will provide the same image, including the bulge, but only viewed at the opposite angle.
You will now have two meshes that form the bulge shape. To combine the meshes into one shape, the opposite array will have to be updated so that triangles along the edge have the correct opposite values stored.
And here you have it, the completed 3D form of our original 2D polyloop.